In this video, I'm going to describe and explain vector functions. I'm going to explain vector functions with examples that use vector functions to describe the position of a moving particle. These examples will involve using parametric equations, so I'll begin by discussing these. I'm going to do this using an example involving a particle moving through the xy plane. For a particle moving through the xy plane during a time interval I, we can describe each of the particle's coordinates as a function of a third variable, t. We can describe the particle's path with a pair of equations, x equals f of t and y equals g of t, for values of time t on the time interval I. We can describe the particle's position on the x-axis as a function of time using the equation x equals f of t. And we can describe the particle's position on the y-axis as a function of time using the equation y equals g of t. The points xy equals f of t, g of t for values of time t on the interval I form the curve on the xy plane that is the particle's path. For the example shown to the right, the function f of t is equal to 3t, the function g of t is equal to t squared, and the time interval I is the closed interval from 0 to 4. The points xy equal to 3t, t squared for values of time t on the closed interval from 0 to 4 form the curve on the xy plane that is the particle's path. Values of t on the closed interval from 0 to 4 are values of t which are greater than or equal to 0 and less than or equal to 4. The variable t is a parameter for the curve. In this example involving motion, t represents time. The particle starts at point 0, 0 at time t equal to 0. It moves along the path as t increases. And it's at point 12, 16 at time t equal to 4. The point 0, 0 is the initial point of the curve. The point 12, 16 is the terminal point of the curve. This brings us to a definition for a parametric curve and parametric equations. If x and y are given as functions, x is equal to f of t and y is equal to g of t over an interval of t values, then the set of points xy equal to f of t, g of t defined by these equations is a parametric curve. The equations x is equal to f of t and y is equal to g of t are parametric equations for the curve. I'll now use our current example to describe the position vector. The vector r of t from the origin to the particle's position p, f of t, g of t at time t is the particle's position vector. The functions f of t and g of t are the component functions of the position vector. We can describe the position vector in component form as left angle bracket f of t, comma, g of t, right angle bracket for a given time t. I'll update this on the diagram to the right. We can also express the position vector at time t as f of t I plus g of t j for a given time t. This expresses the position vector as a linear combination of standard unit vectors I and j. We can think of the particle's path as the curve traced by r during the time interval I. This equation, now highlighted, defines r of t as a vector function of the variable t on the interval I. A vector function on a domain is a rule which assigns a vector to each element in the domain. When we say domain, we're referring to the set of allowed input values to the function. Here, the vector function r of t is assigning a position vector to each value of time t on the interval I. To distinguish between vector functions and real-valued functions, we refer to real-valued functions as scalar functions. The component functions of r of t, which are now highlighted, are scalar functions. When a vector function is defined using component functions, we assume that the vector function's domain is the common domain of the components. So in this example shown here, we assume that the domain of the vector function r of t is the time interval I. I'll explain vector functions further using our example. In this example, the function f of t is equal to 3t, the function g of t is equal to t squared, and the time interval I is the closed interval from 0 to 4. The equations x is equal to 3t and y is equal to t squared on this time interval are parametric equations for the parametric curve shown to the right. The vector function r of t is equal to 3t t squared given in component form and equal to 3ti plus t squared j given in terms of I and j. I'll update this on the diagram to the right. We can describe the particle's position p at a time t as the point 3t t squared. R of t is a vector function which assigns a position vector to each value of time t on the closed interval from 0 to 4. The functions f of t is equal to 3t and g of t is equal to t squared are the component functions of the vector function r of t. For time t equal to 1, the vector function r of t outputs the position vector r of 1, which is equal to the vector 3 multiplied by 1, 1 squared, which is equal to the vector 3, 1. This position vector is now shown on the diagram to the right. We're not just limited to integer values of time t. In this example, the vector function r of t assigns a position vector to every value of time t that is greater than or equal to 0 and less than or equal to 4. For time t equal to 2.5, the vector function r of t outputs the position vector r of 2.5, which is equal to the vector 3 multiplied by 2.5, 2.5 squared, which is equal to the vector 7.5, 6.3. This vector is now shown to the right. I'll explain vector functions further with another example, this time involving a particle moving on a circular path in the xy plane. We can use the equations x is equal to f of t and y is equal to g of t to describe the particle's path for values of time t on the time interval I. We can use the equation x is equal to f of t to describe the particle's position on the x-axis as a function of time. And we can use the equation y is equal to g of t to describe the particle's position on the y-axis as a function of time. The vector function r of t is equal to f of t, g of t in component form, and it's equal to f of t I plus g of t j in terms of standard unit vectors I and j. The functions f of t and g of t are the component functions of the vector function r of t. The vector function r of t assigns a position vector to each value of time t on the time interval I. For this example, the function f of t is equal to cos t. The function g of t is equal to sin t. And the time interval I is the closed interval from 0 to 2 pi. The equations x is equal to cos t and y is equal to sin t on this time interval are parametric equations for the parametric curve shown to the right. When we substitute f of t is equal to cos t and g of t is equal to sin t into the vector function r of t, we get r of t is equal to cos t sin t in component form, and it's equal to cos ti plus sin tj in terms of I and j. The vector function r of t assigns a position vector to each value of time t on the closed interval from 0 to 2 pi. At time t equals pi over 4, r of pi over 4 is equal to cos pi over 4I plus sine pi over 4j. In this example, I'll describe vectors in terms of I and j, as opposed to the previous example, where I mostly used component form. If we wanted to, we could describe these vectors in component form instead. Looking at this vector now highlighted, cos pi over 4 is equal to the square root of 2 over 2. And sine pi over 4 is also equal to the square root of 2 over 2. So cos pi over 4I plus sine pi over 4j is equal to the square root of 2 over 2I plus the square root of 2 over 2j. This vector is now shown to the right. It's a position vector extending from the origin to the particle's position P at point the square root of 2 over 2, the square root of 2 over 2. At time t equals pi over 2, r of pi over 2 is equal to cos pi over 2I plus sine pi over 2j. Cos pi over 2 is equal to 0, and sine pi over 2 is equal to 1. So cos pi over 2I plus sine pi over 2j is equal to 0I plus 1j. 0I plus 1j is equal to the standard unit vector j. This vector is now shown to the right. It's a position vector extending from the origin to the particle's position P at point 0, 1. I'll calculate one more position vector. At time t equals 3 pi over 4, r of 3 pi over 4 is equal to cos 3 pi over 4I plus sine 3 pi over 4j. Cos 3 pi over 4 is equal to minus the square root of 2 over 2. And sine 3 pi over 4 is equal to the square root of 2 over 2. So cos 3 pi over 4I plus sine 3 pi over 4j is equal to minus the square root of 2 over 2I plus the square root of 2 over 2j. This vector is now shown to the right. It's a position vector extending from the origin to the particle's position P at point minus the square root of 2 over 2, the square root of 2 over 2. As the value for time t increases from t equals 0, we can see how the particle moves counterclockwise around the circumference of the circle. And we can see how the particle's path is the curve traced by the vector function r. Before discussing limits of vector functions, I'll briefly revise limits of functions. We can think of the limit of a function f of x as the value that the function approaches, as x approaches a value x0. We write this in the following way, and we read this equation as f of x approaches the limit L as x approaches x naught. For example, for the function f of x is equal to 3x, 3x approaches the limit 6 as x approaches 2. As the value of x gets closer and closer to 2, the value of 3x gets closer and closer to 6, no matter how close the value of x gets to 2. I'll now cover limits of vector functions. Limits of vector functions are defined in terms of their scalar components. For a vector function r of t equal to f of t I plus g of t j, if f of t approaches the limit L1 as t approaches c, and g of t approaches the limit L2 as t approaches c, then r of t approaches the limit L as t approaches c, and this vector L is equal to L1i plus L2j. I'll demonstrate this with an example. For the function r of t equal to cos ti plus sin tj, the limit of r of t as t approaches pi over 3 is equal to open bracket the limit of cos t as t approaches pi over 3, a close bracket I, plus open bracket the limit of sin t as t approaches pi over 3, a close bracket j. Cos t approaches the limit cos pi over 3 as t approaches pi over 3, and sin t approaches the limit sine pi over 3 as t approaches pi over 3. So r of t approaches the limit cos pi over 3i plus sine pi over 3j as t approaches pi over 3. Cos pi over 3 is equal to a half, and sine pi over 3 is equal to the square root of 3 over 2. So r of t approaches the limit half I plus the square root of 3 over 2 j as t approaches pi over 3. Once I'd calculated the limit of its component functions as t approaches pi over 3, I was able to calculate the limit of the vector function r of t as t approaches pi over 3. Before discussing continuity of vector functions, I'll start with a less mathematical description of continuous functions, and then give a more mathematical description. We can think of a continuous function as one that we could draw with a pen on a page with an unbroken line, without lifting the pen from the page. Now shown below is a plot of the function y equals f of x equals sine x on the closed interval from 0 to 2 pi. This function is a continuous function. The function's output values vary continuously with its input values. They don't jump from one value to another value without taking on the values in between. It is continuous at every point of its domain. Now shown below is a plot of the function y equals f of x equals sine x for values of x not equal to pi over 2, and y equals f of x equals minus 1 when x equals pi over 2, on the closed interval from 0 to 2 pi. This function has a point of discontinuity at x is equal to pi over 2. We cannot draw this function with an unbroken line. This function is not a continuous function. It is not continuous at every point of its domain. I'll now use limits to describe continuity of functions. A function f of x is continuous as an interior point C of its domain if f of x approaches the limit f of c as x approaches c. A function f of x is continuous as a left endpoint A of its domain if f of x approaches the right-hand limit f of a as x approaches a. A function f of x is continuous as a right endpoint B of its domain if f of x approaches the left-hand limit f of b as x approaches b. And a continuous function is one that is continuous at every point of its domain. I'll now describe continuity of vector functions. A vector function r of t equal to f of ti plus g of tj is continuous at a point t is equal to c if and only if its component functions f of t and g of t are continuous at t is equal to c. A vector function r of t is continuous if it is continuous at every point of its domain. Now shown to the right is a plot of the vector function r of t equal to cos ti plus sin tj for values of t on the closed interval from 0 to 2 pi. The component functions cos t and sin t are continuous at every point of the vector function's domain. So this vector function is a continuous vector function. If one or more of the component functions had a point of discontinuity on the vector function's domain, then this vector function would not be a continuous vector function. To summarize, in this video, I've discussed parametric equations and parametric curves. I've described and explained vector functions using examples of particles moving in the xy plane. And I've covered limits of vector functions and continuity of vector functions. If you found this content useful, please subscribe to the channel to receive more content. Thank you very much for watching this video. See you next video.